Okay, so I'm recording now. Yeah, it won't get your faces, it will get your voices. And so we want to talk about the stuff we did on Tuesday. So this is Intro to Equilibrium. Right, and so we had this kind of funny question come up of, the example I started with was H2O liquid going back and forth to H2O gas. And we said, look, we could write this down as two separate equations of H2O liquid to H2O gas and H2O gas to H2O liquid, but we recognize that it's essentially two sides of the same coin. And there's some back and forth between these two, energetically speaking, from this idea of delta G. Right? Delta G is going to tell us something about how this reaches a balance between it going forward and it going backwards. Right? That idea of enthalpy and entropy. This H2O in the liquid state has some enthalpy and entropy associated with it. This H2O in the gas state has some enthalpy and entropy associated with it. And as we go back and forth between the two, there's some enthalpy and entropy related to this overall reaction. And so there's going to be some amount that this goes forward and some amount that it goes backwards. Now, up until now, most of the chemical reactions that we have looked at, I'll write a different example. Most of the chemical equations we've looked at have been all the way towards products. So if we looked at something like HCl plus NaOH goes to NaCl plus H2O. Right? This, if I drew this, if I drew the arrows to try and communicate how much it goes forward and backwards, this would be, I would draw a massive arrow forward, and I would draw an arrow probably about that size backwards, right? That little dot's the arrow backwards. Right? And most of the reactions we've looked at, we haven't had to worry about this forward backwards, like we've only drawn the arrow forward, because up until this point, most of the reactions we've looked at have been these types of reactions that are so product favored. They're so product favored, we haven't worried about any balance between the products and reactants. Anything we would consider, this chemical reaction, I think it's something like 1 billion times more products than reactants. So I would have to have accuracy down to like 10 to the positive, like 10 to the, like 9 decimal places in order to start to worry about this forward and backwards. And I'd have to have equipment that could measure that. What became more interesting is the idea of this, some reactions going forward and backwards means that I can open up a whole new category of chemical reactions we haven't looked at before, that we can start to think about in terms of how they behave. So the example I'll use, this is one of the most typical examples. Right? If I put this compound, acetic acid, it's a weak acid, into water, it develops some amount of equilibrium. Right? Again, I drew these arrows. Normally we just draw the arrows, we just draw double arrows. I'm trying to draw, as we're learning about it, I'm drawing my arrows kind of in some proportional way. And I drew my arrows the wrong way. Right, so we have some, like, this is how we normally draw it. We just draw, like, forward and backwards. We got to think about how this reaction, the energy that pushes it forward and the energy that pulls it backwards. The energy that pushes it towards products and the energy that pushes it towards reactants. And I drew it wrong because it turns out that this reaction is only a little bit going forward, mostly. So this reaction is going to stay mostly as reactants. I'm getting spam calls. right? So there's some equilibrium that's going to happen in how this goes forward and backwards. And the question becomes, how do we talk about it? How do we make sense of how much goes forward and how much goes backwards? And we introduced this idea of, well, let's keep track of how much products there are and how much reactants there are. So we introduced this idea, this ratio, this idea of the percent of how much products and how much reactants. And we said there's a scale to this where I can go 0% products, 100% reactants, or I can go all the way to the other extreme where I can go to 100% products, 0% reactants, and someplace in the middle is 50% products, 50% reactants. Right, and if I've got a way to measure my products and I've got a way to measure my reactants, I can keep track of how much products and how much reactants there are. Right, so I have to have a way to measure acetic acid, acetate anions, and hydronium ions. I have to be able to measure all three of those things. But if I can measure those, I can keep track of my chemical reaction, and I can see, as the reaction goes, how does this value change? How does this value change as the reaction goes? Right? And then where does it stop? Right? So there's two different questions we're trying to ask. How does this value change, and where does it stop? And because we get tired of pointing and looking at this thing, we give two different letters, one for this one of how it changes, and another letter for where it would stop. Right, so this is going to be what we call Q. It's called the reaction quotient. And so that will be the thing that we track. And then we've got another value that looks very similar, but it gets a special subscript because this equation is only going to be true at the equilibrium values. So that is to say, how much this reaction is happening. There's still things going on. When I say stops, what I mean is it appears to have stopped to us. Really, there's still stuff changing, but every time we look at it, it looks the same because it's going forward as much as it's going backwards, and so no concentrations are changing to us. Chemical compounds might be still switching around, but every time we look, every time we measure it, we measure the same values. That's equilibrium. So out of all of these possibilities, for this chemical reaction, I happen to know it's a really small equilibrium constant, right? That would be that single value, someplace over there, that would be the 1 KEQ value. Whereas the Q value, this reaction quotient, how much products and how much reactants, we can just control that with experiments, right? We can dump in as much of this and as much of that as we want experimentally. And just dump stuff in. But nature, energetically, is always going to push it to reaching some equilibrium, some proper ratio that's going to minimize the energy between the reactants and the products. So that's the kind of new idea that we were starting to get to, was how do we tie this idea that reactions can go both directions, because we've seen reactions from our Hess's law thinking, from our delta H's, we've seen we can write reactions backwards. We can still calculate delta H's, delta S's, and delta G's for forward or backwards. So what happens when we start thinking about the forward and the backward together? And there were kind of two wild equations that come out of this thinking that I pretty much just said, hey, trust me on these. And that's going to be how we formally write down Q for a particular chemical reaction. So my Q equation is going to be products over reactants. That's going to be my CH3COO minus concentration times my H3O plus concentration divided by my CH3COOH concentration. Each of these would be to the power of 1. We usually don't write the ones in there, but that's because this is a 1, this is a 1, this is a 1. So it goes to the power of the coefficients. Kind of a boring example because they're all 1s. Similarly, I can write down an equilibrium expression for this that's going to look exactly the same except for one important difference. CH3COO minus H3O plus divided by CH3COOH, all to the 1s again. The important difference, these values that I have written in blue, any numbers, right? Q is just keeping track. These values I have in green, this equation is only going to be true at equilibrium values. So once the forward, the backwards, once it looks like nothing is changing anymore, once it hits some stable balance of the reaction, that's the only time that KEQ equation is valid. So we've got some starting spot, Q, initial conditions. We're going to go through some amount of change, and as we go through that change, we'll eventually reach to some equilibrium position of our reactants and products. That will not be zero reactants. Again, everything we've done up till now, we've just said limiting reactant goes to 0. With this energetic idea, that's never actually true. Nothing actually goes all the way to 0. It might go so small that it's effectively 0, right? It might be 1 times 10 to the minus 15 molarity, or like 1 times 10 to the minus 15 moles per liter. Effectively 0. Smaller than we could measure, but not actually 0.
Wait, so equilibrium never hits 0, or what never hits 0?
Our amount of reactants never hits 0. So the stoichiometry we've learned in the past, is it completely wrong? Can we not do stoichiometry with limiting reactants where limiting reactants go to 0? No, that still works a lot of the time. As long as we're in a situation where the equilibrium is like, so for this black reaction, the equilibrium's like over here. It's like 99.999999999% products. In that situation, yeah, just do the stoichiometry limiting, our reactant approximately goes to 0. But for this equation in blue, where the reaction doesn't go forward that much, there's an equilibrium balance point between the products and the reactants where the reactants don't go to 0. There's no limiting reactant. There's an energetic balancing point. So how do we find that energetic balancing point? Well, there's an equation, right? I said that all of this depends on that delta G. There's a new equation that we have that relates this equilibrium idea I think there's a negative there. I have to double check. I just blanked on my equations. Yeah, there's a negative. Okay, cool. So that delta G equation, delta G with the superscript 0, we started talking about the superscript 0 a little bit. We'll talk more about it on Tuesday, tomorrow, right? That delta G standard, that's what the superscript 0 means, is standard, is negative RT ln KEQ. So our equilibrium constant comes directly from our delta G calculations. So if we can calculate delta G from delta H and delta S at a particular temperature, we can figure out how this chemical reaction goes to equilibrium. Or if we do an experiment and we figure out what the equilibrium constant is, then by measuring like the concentrations of the acids and the bases and everything, then we can figure out what the delta G for the reaction is. So if we can figure out delta G, we can then calculate KEQ. Or if we can experimentally measure KEQ, then we can figure out delta G. These two things are going to relate to each other. And that's about where we got to in class on Tuesday. So we still have a lot to do. There's a lot of key terms. There's a lot of vocabulary. Key terms of vocabulary, 1 through 5, how many days? I'm expecting all zeros because we just had a midterm, but tomorrow you can surprise everybody and be 2s. If you do today and tomorrow, everyone else is going to be like, wait, you did stuff. It'll be good. So one of the things that we're going to do tomorrow in class is we're going to say, okay, how do we put these two ideas together? Right? Our thermodynamic idea of delta G versus our new equilibrium idea of delta G. Right? These equations, these equilibrium equations that we're using, the fact that this is concentration of products over concentration of reactants with superscripts to the, with coefficients becoming superscripts, our delta G is this negative RT ln KEQ, and it's somehow going to relate to this other delta G thing we've done. There's a lot of stuff we're glossing over that's hidden inside of. There's a lot of math, statistical dynamics, like there's a lot going on. And that's where I said, hey, just believe me for this equation, believe me for this setup. Some of it makes sense if we're good at using like natural logs, and we write down all of our stuff for how we do sum of products minus sum of reactants, where the coefficients are multiplied out front. When we do exponentials, all the additions become multiplications. That's why it's multiplied products divided by multiplied reactants, right? Some products minus is a division, some reactants, so it has some sense. The multiplication of the coefficients out front, coefficients become exponents in that situation, so all of that kind of connects. We're not going to have to make those connections, right? Unless you really want to, right? Trust or make the connections, right? They're there, and we could do some work to kind of be like, oh, this stuff that just dropped on us isn't really coming out of nowhere. It's this interesting balance of energies between reactants and products, and how our Q and our KEQ relate to each other. But this will get us started. So at this point, you can probably, do you see, what do you think is going to happen next with these equations that I just wrote down in green? I've got 2 equations for delta G standard.
You're going to equal them to each other?
Yeah, we're going to equal them to each other. We're going to do a little division. I feel like doing this, and then we can move on to something else, or I'll ask others. So we're going to set them equal to each other. I'm going to have negative RT ln KEQ is equal to delta H minus T delta S. And then I'm going to do a little division. I'm going to end up with ln KEQ is equal to negative delta H over R 1 over T minus, plus delta S over R. And the reason I like this one, I put my superscript 0 in the wrong spot. What does this make you think of? What's the next thing? This is the last thing we'll talk about. We're going to do this tomorrow in class as well. What's your favorite equation for a graph?
Linear?
Yeah. What's the equation for a line?
Y equals mx plus v.
We can make a linear plot out of this. If we measure the equilibrium constant at many different temperatures, we can make a linear plot to figure out delta H and delta S. Or if we know delta H and delta S, we can use many different temperatures to find the equilibrium constant.
I'm confused on like how the 1 over T.
Oh, that's because the negative RT, I divided the negative RT over. right, this negative RT, notice it's just ln KEQ here, so I divided that over, so it's RT on bottom, negative RT. The T's cancel out over here,
Okay.
right? And so that's what allows us to set this up as like a linear plot. And we love it when there's linear plots because now I can see KEQ, natural log of KEQ on my y-axis, 1 over T on my x-axis. I can figure out delta H and delta S. And that's the Gibbs lab that we're going to be doing tomorrow. Now, there's some important thinking we have to do around what this KEQ means in the chemical system we're looking at. And so that's why part of why I started with this information of what's Q, what's KEQ. Because we're going to pick a particular chemical reaction, not this one. This is what we're going to do next. We're actually going to do this experiment. Oh, actually, no, we do something besides this, but we're going to do something that's acid-base next. We can start changing our subscripts to kind of give suggestions of what chemical reactions we're looking at. We use Ka, so this is an acid reaction, so we use Ka when we're looking at acid equilibrium. We use Kb when we're using base equilibrium, just because then like the B tells us like, oh, it's a base. We use Ksp when we're looking at solubility, right? So it's still a K, it's still an equilibrium, but the Sp tells us, oh, we're looking at one particular chemical reaction where we're going to write it. Because notice, with this double arrow, what I write as reactants and what I write as products is a choice we make. Like every time we write down a chemical reaction, all of us now, we can pick whatever we want for reactants and whatever we want for products. If we all pick different things, I mean, it's really 50-50, right? If we've got the same chemical reaction, right? If we pick different things, our math will be different, but our end result will be the same. So to make it a little bit easier, we usually set it up where it's like, hey, what if we all just picked the same reactants? Even though we know it's an equilibrium, we could pick either one as the reactants. We pick the same reactants going to the same products, so we all do the same math, right? K, when we do that subscript A, Ka, we're particularly talking about this, where we've got water with a weak acid going to an anion and that H3O+. That's every Ka is. We agree on the reactants, we agree on the products. Now we're all doing the same math, we're all going to get the same result. If you decided to do a different setup, you're going to do different math, you're still going to get the same result. Because it's equilibrium, right? It doesn't matter which direction we go, it's just how easy the math is. Usually we set it up so the math is easier, but if you want to do harder math, you can set it up the opposite way, and it works fine too. Right? KSP is going to be specifically solid going into water makes ions. Right? Not ions making solid, solid making ions. Again, it's equilibrium. It can go both directions. SP just means we've agreed to write the same reactants so that our math is the same, our end result will be the same. If you write it the opposite direction, your math will be different, your end result will still be the same. And so those subscripts are just to help us know how we're all doing the same setup, all doing the same math. Was that good? Was that kind of what you were looking for?
Yeah.
Yes.
Remind me, Pamela, well, yeah, Pamela, I know your name, but I shouldn't.
Yeah, I just had a question about, because you know he said like subscript, like 0, like standard.
Mm-hmm.
I know you explained like the difference between standard and just like the other one. Can you just give me a refresher on it?
Yeah. Is it okay if I erase the stuff at the top of the board to do that?
Yeah. Oh, I'm done now.
Yeah.
Okay. So, this is going to get into some details. I went over it pretty quickly at the end of class last time, and it's definitely something we're going to have to spend more time on. But there's essentially 2 different delta G's. There's 2 different delta H's and there's 2 different delta S's. Up to this point, we've actually almost always been working with delta G standard. And I've probably been relatively lazy about whether I've written my superscripts for standard conditions or non-standard conditions. Right, so that's non-standard. and this is standard, right? But now that we're talking about equilibrium, we've got this Q and this KEQ, standard versus non-standard actually is going to matter a whole lot. So when we talk about non-standard conditions, well, let's talk about standard conditions first. Standard conditions is going to be 1 atmosphere pressure, 25 degrees Celsius, and the new thing, concentrations equal to 1 molarity. Remembering that bracket, these brackets stand for concentration. So this is concentration H3O plus, concentration CH3CO minus, right? So my concentrations are 1 molarity. That's going to be our standard conditions. And so when we talk about delta G standard, we're really talking more or less about these conditions being true. So essentially, right, this gives us a starting spot for our Q. Right? Our Q could be any value. If our Q is any value, we don't know if we're starting all the way over here, if we're starting here, like where we're starting, and how we approach KEQ. If we start from standard conditions, we're pretty much always going to be starting at the 50-50 point and seeing how we approach KEQ. So, for example, if we were looking at the weak acid reaction with acetic acid, if I started at standard conditions, I would have to move this direction in order to get to equilibrium. And so this gives me a way to talk about the fact that I am going to be moving towards reactants. It's going to be So the fact that the KEQ is over here with more reactants than products, that makes this a reactant-favored situation. But there's a difference between being reactant-favored and going towards reactants. Right? From standard conditions, I'm going to go towards reactants. I'm going to be reactant-favored. However, if I had a situation where I started with 100% reactants, I would still have to go towards products a little bit, even though I'm still going to end up with more reactants than products. I'm still reactant-favored. If I start with 0, I still have to go towards products to get there. The problem with non-standard conditions is you could be starting anywhere along this line. Standard conditions, we're always going to start kind of in the same spot and think about how we move. Same thing. Now notice for that strong acid, strong base situation, where we've never had to talk about this idea of Q and KEQ, first off, look where the black arrow is. Am I product favored or reactant favored?
Product favored.
Super product favored. If I start at any point, if I'm looking at non-standard conditions, which direction? If I start at 0 products, which way do I have to go to get towards that equilibrium? Towards reactants. Where do I have to go? Towards products. Towards products. You pointed the right direction but said the wrong word. I knew you were thinking the right thing. Right? So no matter where I start for that reaction, it doesn't matter. I still have to go towards products in order to get to this equilibrium point. Because this equilibrium point is so dramatically far over towards like almost all products. That's why we've never had to worry about this before. Almost every reaction we've looked at up till now has been this type of situation where it doesn't matter where we start, we go towards products, we end up with all products, we end up with reactants going to 0. Now we've got these types of situations where it matters where we start, it matters whether we're product favored or reactant favored, and whether we're going towards products or towards reactants. Because we're starting at any point. So in this delta G standard situation, if all my concentrations are 1 molarity, my Q is always equal to 1. Because I'm going to have 1 times 1 divided by 1 is 1. If I have 1 times 1 squared divided by 1 times 1, it's still 1, right? It's just ones and ones. Doesn't matter if you square it, double it, like well, it matters if you double. Square it, cube it, multiply it multiple times, right? Q is always going to be equal to 1 in this delta G standard. Delta G is really kind of more like that energy of spontaneous, non-spontaneous. We're not going to be, delta G standard kind of gets us towards products, towards reactants, product favored, reactant favored. delta G is spontaneous, non-spontaneous. How much extra energy is there? So they kind of address two different situations. So this G is positive, or is non-spontaneous, negative, or spontaneous. This delta G standard is going to get us let me think about this. I gotta do the math. I haven't looked at this in a while. So if my KEQ is less than 50-50, that means my KEQ is gonna be bigger on bottom, smaller on top, which means it's gonna be less than 1. Natural log of something less than 1 is negative. So if we are reactant favored, that delta G standard is gonna be positive. For product favored, that delta G standard is going to be negative. Because we'll have natural log of a large number, that's going to be positive times the negative. Yep. So it shifts. The important thing that's going to happen between class last Tuesday and class this Tuesday is our language is going to have this dramatic shift from talking about non-spontaneous and spontaneous to talking about product favored versus reactant favored. We're going to shift to talking about things in the context of the chemical reaction rather than just the context of the energy. So there's going to be this kind of important switch. I'm not going to get into the extra equation, but that's the short version of it. Is what's the sign of delta G? That gets us spontaneous versus non-spontaneous. What's the sign of delta G standard? That gets us product favored versus reactant favored. And then we can also add in an extra bit of, the other thing we can do is we can do Q versus KEQ to get towards products or towards reactants. Right? And that was the kind of thinking I was doing here on this line. So we end up with kind of 3 different structures that we're going to think about. Spontaneous versus non-spontaneous, that's what we've already been doing. We're going to shift to talking about product favored versus reactant favored from standard conditions. But then we can also talk about, because how often do we pour, like notice, to be standard conditions, I need 1 molarity of my reactants and 1 molarity of my products. How often do we start perfectly in the middle with 50-50 reactants and products and then do our reaction from there?
Not often.
Like never, right? We almost always start at 100% reactants, 0% products. So we need to know how we compare non-standard conditions to figure out how the reaction proceeds as well. So that's where we add in this Q versus KEQ bit to talk about whether we're going towards products or towards reactants. So those are the 3 ideas that we bring in. Talk about this. Other questions? Okay. No other questions on this stuff?
No, I think
Cool.
it's just
I'm going to go ahead and stop recording. I'll post this video.